The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
As I mentioned in the end of the last session, that we're going to be talking about now about the transverse modes of lasers. Now these are what we call undesirable, this is an undesirable behavior of lasers. There are very few applications that take advantage of these transverse modes. So let's talk about them, and also we have a little demonstration to show you these modes and some of their characteristics. Okay, so the topic now is then transverse modes, and then we remind you of what we did before. You know, typical laser cavity with two curved mirrors. We have the output coming out, which is a single spot, that Gaussian spot that we get, and we're used to it because most lasers, that's what they put out, is that single spot with a peak intensity in the middle. Now let's see what else lasers can do. Well, turns out that some lasers will give you, instead of just a single spot output, will give you two spots, and sometimes more than two spots. And in most cases, the modes are there simultaneously. So it's not like this separate mode. This is what we call the higher order mode, or 0-1 mode, or so on. We're not going into that in this course. But this is called the 0-0 mode, which is the lowest order mode. Now, sometimes I say we get mixtures of these and other higher order modes, and they're a mess. Now, before I go to the demonstration, I want to discuss some of the properties of these modes with you so that you appreciate the demonstration a little bit more. Let's look at, aside from the intensity distributions, which was obvious, there's also the frequency issue. There's a spectrum issue. So let's look first at what we call the lowest order mode. And again, we have the cavity modes for that. And if there's enough gain to oscillate here, then you get what we call the 0-0 mode output associated with the 0-0 mode cavity resonance. Now, when this other guy oscillates, okay, because again, this fellow satisfies the boundary condition, just like this one here, but the mode has essentially a hole in the middle. Essentially, it's two spots. Now, this particular mode does not have the exact optical length of this one for its cavity. It has a slightly, it looks like the cavity for this one, even though it's exactly the same, but optically it looks slightly different than that one, which means that the optical length is slightly different, which means that the resonances, the cavity resonances, are slightly shifted for this one from that one. They're still C/2L apart, there's no problem, but the exact phase shift, you know, between one mirror and another is slightly different for the transverse modes. So again, if there's enough gain here to oscillate, then this one will also oscillate. Now you get two frequencies oscillating, when normally, you know, we would expect only one, because there's only one cavity resonance under the gain curve. So in this case, you get two. Now, if you have other transverse modes, if you have this is what we call 1-0, 2-0, 1-1, 2-1, and so on. These are all shifted from one another, and they generate all sorts of laser frequencies. Now, so it can be a mess. So the spectrum of the laser output, instead of being single frequency, now you see all kinds of modes and all kinds of intensity distributions. If you want a formula for this, as I say, in this course I'm not using any formula, but this one is difficult to keep away, and that basically will give you the resonance frequency for any cavity mode you want in terms of the transverse mode number. Q is the same Q we had before, what we call the longitudinal mode number. M and N are the transverse mode numbers, you know, in the X direction and the Y direction. And this is the formula. I don't know whether it's worth going into it, but basically it's again C/2L times Q. That's what we had before. And on all this other stuff is because of the transverse modes. So for a given transverse mode, depending on what M is and N is. Like this one here, the 2 spots is 1, 0 or 0, 1, depending whether it's in the X direction or the Y direction. And the 3 is in a horizontal line is 2, 0. The 4 here is 1, 1, and so on. So by substituting M and N from whichever mode you have, and then plugging into here, and this very simple formula, 1 minus L over rho 1, where L is the separation between cavity mirrors, rho 1 is the curvature of one mirror, and here's the curvature of the other mirror. And when you do all this, you find that you can calculate the frequencies of these transverse modes, and the laser will oscillate at them. But if you were able to isolate, let's say you isolate this one, like we'll do in the demonstration, indeed you'll see the basic cavity modes that look like this, C over 2L apart. And also in the demonstration, we'll make this one oscillate with this one and others, and then you'll see all sorts of modes. Now, as I say, there are not many applications that take advantage of all these modes. There is 1 or 2, but we don't want to bring them up at this stage. Most lasers would like only this mode. So we need to get rid of these. Okay, so in order to get rid of them, what we have to do is the following. We put an aperture inside the cavity. It doesn't have to be in the center. It can be elsewhere. And this aperture, what it does, it starts to cut into these transverse modes. Because these transverse modes, if we do the calculation, they're always bigger in size than the lowest order mode. So when we start putting an aperture inside, we provide loss, a little bit of loss for these guys. And if there's enough loss so that the gain is not enough to laze, then they'll drop out. While this one here, even though we cut into them, if we don't cut too much into this one, into the lowest order mode, then it can still survive. Maybe it'll be less intense, but it will survive. But this one will go out, since all the transverse modes are bigger than the lowest order mode. All right, so this is one way of getting rid of these transverse modes. And there are also other clever techniques of getting rid of them, but this is the simplest to understand. So we have to do something, we have to put an aperture there to get rid of them, otherwise they'll oscillate if there's enough gain for them to oscillate. All right, so now I think we're ready to look at a demonstration that demonstrates these transverse modes, at least in terms of intensity, and also will demonstrate the spectrum, the modes that are associated with these modes, either when they're all together or when they are separated. And we have a nice little technique of separating out one higher order mode, then we'll show it to you and show its spectrum. So I think this demonstration is a lot of fun because lasers with transverse modes are not readily available, because usually, as I say, manufacturers make sure that their lasers only oscillate in one transverse mode. So I think now we're ready to appreciate this demonstration. In previous demonstrations, we showed the laser beam to be a very simple beam with a single spot in the transverse direction. Now, most lasers actually put out a beam like that, just one spot in the transverse direction, and the intensity distribution is Gaussian. It has very nice properties, and that's why it's a very popular beam from a laser. Now, a laser can also put out other intensity distributions because of the existence of transverse modes, which means that the beam would look very spotty. Sometimes it can look like a donut with darkness in the center. You can also make it look like 2 spots, 3 spots. You can make it look like a flower, and so on, all because of the existence of transverse modes. Now, in this demonstration, we got a special laser for you that can exhibit these transverse modes. And the setup is here. We have our usual discharge tube, except in this case, the bore diameter is a little bit bigger than in previous demonstrations. The diameter here is of the order of 2 millimeters, 2.5 millimeters or so, while before the bore diameter was about 1.5 millimeters. One mirror is attached to the discharge tube over here, and the other end of the discharge tube has a Brewster window, so that we can place the second mirror over here. This mirror here is curved about 60 centimeters of a radius of curvature, and the mirror here is a flat one. The transmission of the mirrors is very small, and so that the output light is not going to be as bright as we would like it, but hopefully we'll be able to see the transverse modes. The beam then from the laser will come out over here, and then we'll reflect it by this mirror, and then this mirror into a lens. Here we expand the beam, and then the expanded beam then will fall onto the screen over here. So now let me turn on the laser, and we count up to 7 or 8 seconds or so, and here is the laser on. And the output then from the laser is weak, I know, but you might be able to see it. Here's the output from the laser, and then we're going to reflect it, as I said before, by this mirror to the lens, and then onto the screen. And now we'll have one camera look at the screen, so we can look at the transverse modes, and another camera can look at my hands adjusting one of the mirrors to change the number of modes and the intensity distribution that you will see on the screen. Now here, as you can see, the beam looks like a donut mode with no field in the center, and my hand, you can see in the lower right hand corner, adjusting the mirror mount. Now here I'm going to start now adjusting, and then you can see that the intensity distribution varies quite a bit. Here we are. Here you can see very complicated kind of pattern. Here's another one with 2 dark spots, single dark spot, and here is looks like a flower. Nice, pretty little patterns, and these are all due to these transverse modes. Now what you're seeing here is a mixture of transverse modes. They're not necessarily pure ones. That means just a single transverse mode by itself. Now here, if I misalign too much and get rid of most of them, here is our lowest order mode, which is called the 0, mode. Now here is the normal kind of laser beam, but in this particular laser setup, I can generate all kinds of other intensity distributions due to the other transverse modes that can be generated in this kind of setup with a larger bore in the discharge tube. It's very pretty. As you can see. Now, as I mentioned before, in most lasers, one wants to get rid of these transverse modes so that we can only have the 0 mode. And when we come back, we're going to show a method of eliminating the lasing of these transverse modes other than the lowest order one. We're going to do this by placing an aperture, a small iris, inside the laser cavity. We have now placed an aperture inside the laser cavity so as to get rid of all transverse modes except the lowest order one, the 0 mode. The aperture is over here when we're placing it in the space between the Brewster window and the second mirror. So here's the aperture, and then by adjusting this knob here, I can then change the size of the aperture. In the meantime, we've also covered this the laser tube here with some white paper so that we don't have too much light to burn the camera. So in case you don't see the discharge tube so well as before, is because we've covered it up. So now let's look at the screen now and see the transverse modes without the aperture stopped down. Here we are. We see we see those transverse modes, or mixture of transverse modes. Now what I'm going to do is I'm going to now reduce the size of the aperture, and let's see what happens. Here I am reducing it. And you can see, let me go back a little bit. Here's some other modes, and then when I stop it way down to about 1 millimeter or so, you can see that I have now the lowest order mode, the 0, 0 mode. Okay, let's do it again. Let me open it up again. Here's the transverse modes, and then as I stop it down, I get rid of all transverse modes except the lowest order. In fact, now I can even adjust the mirror. I can adjust the mirror, and indeed I can move the spot around, but I don't get any transverse modes showing up. So in summary, then by putting a small aperture inside the laser cavity and choosing the diameter appropriately, we can get rid of all transverse modes except for the lowest order mode. Now, most commercial lasers either have an aperture like that inside the laser cavity, or have the bore size of the laser amplifier so chosen so that only the lowest order mode would laze, and would very difficult to have the other transverse modes laze also. And that's why most commercial lasers put out that lovely single spot beam. Now, another interesting thing about transverse modes is that their frequencies are different from one another. And that depends on again, the length of the cavity and the curvature of the mirrors. So when we come back, we're going to have the spectrum analyzer set up so we can look at the frequencies of the various transverse modes. We're now ready to look at the frequencies or the spectrum of the transverse modes of this laser using a scanning Fabry-Perot interferometer acting as an optical spectrum analyzer. And here's the setup. The output of the laser, now we take the output from the other end, from the other mirror. We're going to reflect it by this mirror here, onto the scanning Fabry-Perot interferometer. The length of the cavity is about 10 centimeters, which means that the free spectral range will be about 1.5 gigahertz. The output of the scanning Fabry-Perot interferometer then goes onto the scope to display the frequencies of the laser. Now we're going to look at the intensity of the beam, or the transverse intensity distribution of the beam, showing the various transverse modes. And at the same time, we're going to look at the spectrum of the laser light as measured by the scanning Fabry-Perot interferometer. Now here on the screen, now we see on top, we see the intensity distribution of the laser, the transverse intensity distribution, and below we see the corresponding spectrum. What I've done here is I've stopped down the aperture so that we only have the lowest order mode, the 0, 0 mode, oscillating. And on the scope, we see 3 or 4 modes due to the longitudinal modes in the laser, oscillating in the laser. And of course, the number of longitudinal modes will depend on the width of the gain medium. The laser is about 40 centimeters long, which means that the mode spacings is about 375 megahertz. And that's why we get 3 and sometimes 4 modes oscillating within the bandwidth of the amplifier, which is 1.5 gigahertz. And just for fun, what I'm going to do is tap on the mirror gently to shake the cavity, and you can see the contour of the bandwidth of the amplifier, which is about, as I said before, around 1.5 gigahertz. So when I'm not shaking the cavity too much, then we see the modes, the longitudinal modes, stable and quite clearly. So now what I'm going to do is open up the aperture, introduce some high order modes. So what I would like you to do, look at the picture above, and then at the same time look at the spectrum. So I'm just slowly going to bring in. Now you can see already here, even though it still looks like, it appears to be just the lowest order mode, but it isn't, because if you look at the spectrum, you see that we have introduced some new frequencies. And these new frequencies are associated with the transverse modes that are now oscillating. And I can go further now and open up the aperture some more. Here we are. So now you can definitely see a number of high order modes. And look at the frequencies now. There's lots of them, and they're within the bandwidth of the amplifier. And there's one thing nice about having a lot of transverse modes is that you can have a lot more power coming out from the laser because you have more modes oscillating. So here I'll do it again. I'm going to reduce the aperture size and to get the lowest order mode oscillating. See, again, they just get the longitudinal modes of the 0, mode. And now I will introduce the transverse modes again to show that they have their longitudinal mode frequencies are different from the 0, mode. So far, I've only been able to show you a mixture of transverse modes. In fact, the only isolated mode that I was able to show you was the lowest order one, the 0, mode, by itself. And then I showed you a mixture of transverse modes. Now, in the next demonstration, I'm going to use a little trick to isolate a single higher order transverse mode so that we can look at it, and then we can also look at its spectrum. Now, in order to isolate one high-order transverse mode, I'm going to use a very thin wire. The wire will place along the vertical direction inside the laser cavity, and in this way we'll be able to prevent the lowest order mode, the 0, mode, from oscillating, because we'll place the wire right in the center of the 0, mode, so it's providing a lot of diffraction loss for it. But for the next high order mode, the two-spot mode, so-called 1, 0, 0, 1, depending on how you count these modes, then one will be able to oscillate if the wire is thin enough, because this wire is going to be placed right where the field is 0. Now, to make that clearer, I'm going to show it to you on the screen. Before I do this, I want to show you where the wire is placed. The wire is placed in a holder here, and the wire is about 50 microns wide, and it's placed vertically inside the laser cavity. I have an adjustment here. I can move the wire in and out in a horizontal direction. And also I have another adjustment here that rotates the orientation of the wire from, let's say, vertical to horizontal. Now let's go look at the screen and see what sort of transverse mode I've been able to isolate. Now here on the screen you see that I've isolated the next transverse mode. It's called either 0, 1 or 1, 0, depending on how you count these modes. And this consists of essentially two spots with 0 field in between. And remember, I used a vertical wire right in the center of the mode so that this particular transverse mode doesn't need any gain in the middle, and therefore can oscillate with the wire in place. But most of the other modes, like the lowest order mode and so on, cannot oscillate with this wire in there because that provides too much diffraction loss. And that's why we've been able to isolate this one particular mode like this. Now, if we look on the output of the spectrum analyzer, as shown on the oscilloscope below, you can see that we have 2 and sometimes three modes that correspond to the longitudinal frequencies of this transverse mode, just like in the case of the 0, mode. Just clean, single transverse mode. Well, now you've learned something about some of the problems of lasers and what we can do about them. Now I'd like to turn to another topic, and that is the types of lasers. And because we have all kinds of lasers, and I would like in this short course again, without going into too much detail, but just gives you a flavor of how these different lasers function. All right, now there are all kinds of lasers. They're called gas lasers, liquid lasers, solid state lasers, semiconductor lasers, you name it. Chemical lasers, excimer now we have, gas dynamic, even a T laser stands for transverse, electric, atmospheric. There's also a coffee laser, E-beam, electron beam, pump lasers, free electron lasers, and fiber lasers, and now we even have waveguide lasers. All right, there are all kinds of lasers, and so I'd like in this, as I say, in this brief time that I have, is just to give you some flavor. What I would like to do first is to classify. They all depend on the pumping mechanism. And because a cavity is a cavity, but it's the pumping mechanism that makes the lasers different from one another. So we'll classify them then according to the type of pump. And the first pump that I will consider is the optical pump. Now, the optical pump means, let's have a diagram here, means that, again, with our knowledge so far of lasers, here's our three-level system that we talked about, and here's the pump. Now, in this case, the pump is a beam of light, whether it comes from a laser or it comes from, some incoherent light source like a discharge lamp and so on. So, let me introduce you to the way one talks about these things. Here we take the atom A, let's say our gain atom A that has these three levels, and we say there's a photon that comes in, or a light wave that comes in of energy h nu, h being Planck's constant, nu being the frequency. And when you have A plus h nu, when the light interacts with the atom, then if the conditions are right, then the atom goes to A star. A star means that there is a population inversion between some pair of levels. Okay, so that's what this little formula means. It means that the pumping is optical, excites the particular atom or molecule or solid or what have you, and then you generate a population inversion. And as we said earlier, that is the key thing in gain, is you have to have a population inversion. You can have everything else working fine, but if you don't have a population inversion, forget it. So this is the example. Here's a gain medium. It could be pumped, say, by light from the side or light along the axis and so on. That's not the issue. The issue is that it's optically pumped. And there's a population inversion, then the spontaneous emission, then we'll start the lasing, and you'll have lasing as we've discussed before. Now, there are many lasers that that have an optical pump. For example, the first laser, they have a first laser, is the ruby laser. Then the YAG lasers, glass lasers, dye lasers, and today the all fiber optic lasers, waveguide lasers, and so on, they're all optically pumped lasers. Again, with some three-level system or some variation on that, but the pump is essentially is a light pump. Now, here is, for example, here's an example where, let's say, a YAG laser or a ruby laser and so on, where you have essentially a flash lamp, CW or pulsed, that flashes then and sends the right light into the material here that gets pumped and generates gain. In this particular case, it's what we call longitudinal pumping, where the pump laser is outside the cavity and pumps the medium along the axis of the laser beam. And this way, it's a very efficient way of pumping it, because you're not pumping the rest of the medium like here. You're pumping parts of the gain medium that's not being used by the laser cavity. Here, this is efficient, but you have to go through mirrors and so on. So you have to pay attention to problems arising from the way you pump things. Now, I have a demonstration for you, and a dye laser, which is a very widely tunable laser, lots of colors. So I want to show you that. But before I show you that, I want to give you a little background, so you can enjoy the short demonstration even more. The dye laser essentially has the gain medium is a dye, is a liquid that's flowing here, and it's placed at an angle like this, so that, again, at Brewster's angle, to minimize reflection. for certain polarizations, as we mentioned is one of the demonstrations. The pump is an optical pump. So in this case, the pump, let's say, is an argon laser that pumps this dye. This dye could be rhodamine 6G, although there are all kinds of other dyes. And then when the pump, the optical pump is focused into here, then you generate gain, and the gain then will, due to spontaneous emission, will oscillate then within this cavity. Now, if you looked at the bandwidth of this dye amplifier, it's huge. And here I show it to you from green to yellow to orange to red and so on. It almost covers the entire visible range. And so here's essentially the gain curve. Here's the loss line. Now we have all these thousands and thousands of modes that's under this gain curve. And again, as we mentioned before, if there are more gain than loss, then all sorts of modes can oscillate. And so here you can see there are all sorts of colors in these modes. So the light that comes out it has a broad band of colors. All right, because the amplifier is so wide. So the first thing you want to do is that you want to do something about this, because it's nice to have a very broadband amplifier, but if the output consists of all these frequencies and colors, sometimes it's not very useful. So you need to cut down that gain to start with, and be able to tune it. So let's see how you might do it. Here is that cavity again, but what we do here, we put a prism here, or a dispersive element, like a prism or a grating, or I don't want to get into details, but basically something that disperses the colors. And I hope your TV set is set right, so you can see these colors. So here we have these colors broken up into various into the spectrum, to the various colors. And the mirror here is adjusted so that it only reflects one of the colors. So the color that hits the mirror at a normal angle then will be reflected back into the cavity. The color that hits it at a slight angle due to the dispersion here will not go back into the cavity. We'll just miss it, and the laser cannot oscillate, let's say, in the red here, because there is not enough gain to overcome the losses when the cavity is misaligned for the red. But for the orange, or whatever the color that appears on your screen, but for the orange, then the cavity is well aligned, so the orange will be selected. So let's see what it looks like down here in the diagram with the modes. So these are the basic modes of the laser we had before. But the prism, you see, the prism only allows just a few modes, let's say in the orange, to have more gain than loss, and they are the ones that oscillate. All the others, as I said before, the loss is too much because the cavity is misaligned for them, so they do not oscillate. All right. So now, then, by rotating this mirror here, we can select any color we want. In this particular case, of course, we can have several longitudinal modes. But if we put an echelon here, just like in a little earlier, when we put an echelon here, we can even select one frequency. And so we can get out of this huge bandwidth from this dye laser, we can get a single frequency operation, and then we can tune it along the entire gain curve. And the tuning is tricky, because what you have to do in the tuning, you have to tune certainly this mirror here to move the lasing color or whatever, or the lasing bandwidth with respect to the bandwidth of the amplifier. Then you have to tune the cavity, the length of the cavity, so that you have one mode within this bandwidth here. And then if you had an echelon, you have to tune that also. So it gets sort of complicated, but it works. There's a few feedback loops that are involved, and it does work. Now let me now get closer to the demonstration. Now in the demonstration, the cavity is a ring cavity of the dye laser. The cavity of the dye laser is a ring cavity, but it has this jet stream. In this case, it's jet stream because windows are a pain in the neck. So you need where the pump laser is focused into the gain medium. It's actually just a sheet of liquid about a third of a millimeter in thickness and so on, which is flowing transversely here. So there are no windows at all, but still it has to be placed at Brewster's angle. So in here we have a ring, and it has lots of advantages, and right now we're really not going to get involved with that. But basically, it's still another cavity, whether it's a ring or linear cavity, still another cavity, and there's a tuning element in here. This is slightly different from what I have in the previous slide, but it's a tuning element. It's like a dispersion kind of element that separates out the colors, and the output of the dye laser comes out here. So what we're going to do in this demonstration, we're going to take this and scatter it onto a screen, and then tune the element here, and then we can go through the various colors of the laser. And as I say, if your set is adjusted over there, then I'll call out the colors as we do the demonstration. If it's adjusted, then you can maybe see the same colors as we see in the demonstration. If not, well, you get different kinds of colors. All right, so I think now we're ready to look at this fun demonstration of the tuning range of a dye laser. Now I would like to demonstrate to you a very widely tunable laser. In this case, it's a dye laser, with a dye being rhodamine 6G. When pumped with an argon laser, the dye laser can be tuned from light green to yellow to orange, red, and even deep red, using just that one dye. So in this demonstration then, what we're going to do is fire up the dye laser and then tune it so that you can see all these colors right on your screen. Again, you have to be careful and make sure that your monitor is adjusted so that you can see these colors. All right? Now the dye laser is right here behind me, and when we come back, we'll have it all set up, ready to show you those beautiful colors that come out from this dye laser. Now on the left, you see the argon laser pump that pumps the dye jet. Now as we zoom out, we see the entire ring dye laser. So let's look at the dye laser in a more of a close-up. Here's the pump coming into the dye laser. Here it is the pump, the argon laser pump. And pump gets focused into the dye jet over here. The fluorescence from the dye jet then is picked up by mirrors close to the dye jet and then sent around this ring cavity. There's one mirror here, is the laser beam, and there's the other mirror here, and then the other two on either side of the jet. So here's the output of the dye laser. What we're going to do with it, I'm going to pass it through a diffuser to dramatize the display of the color. Here's the output of the diffuser, and I'm going to let it fall onto the screen over there. Now right now, the dye laser is putting out an orangish sort of color, as you can see on the screen. So now I'm ready to tune the dye laser so that we can observe this huge tuning range. And in order to tune the laser, we have inserted a birefringent element over here, and just by simply adjusting the angle using a micrometer, we can tune the wavelength of the laser. But first, let me remind you that the colors you're seeing depend on the setting of your monitor. Right now, you should be seeing orange. Okay, now I'm going to tune either side of orange. Now I have yellow and going towards greenish yellow. Here we are. On the screen I see light green color, and I hope you see that also. So here we are from light green. Now I'm going to tune towards the red. You know, it's becoming yellow. Now orange. And now even stronger orange. Now it's becoming reddish. Now it's nice and red. And getting, in fact, deep red over here. Again, I hope your monitor is going to show you this huge tuning range. Now I will... Well, I hope you like that huge tuning range, because that's very large. It almost covers the entire visible range. And when you think in terms of communications and bandwidth that you need, this kind of bandwidth is incredible. You can put millions and millions of TV channels in a bandwidth like that. Okay, so that was the optically pumped laser. And as I mentioned, there are lots of lasers that are optically pumped. Whether today, you know, we have a lot of semiconductor solid-state lasers that are pumped by semiconductor lasers, and as in fibers, and micro lasers, waveguide, and so on. There are lots of lasers today that are pumped by light, and usually other lasers like semiconductor lasers, argon lasers, and what have you. But they still behave like lasers, and they satisfy the same conditions that we've been discussing. All right, so don't feel that they're going to be too difficult to understand. I mean, the basics are basics. You need population inversion, and that's brought about by the gain, and you need to get rid of the bottlenecks and so on. That's below the lower level, or of the lower level and below. All right, so now let's look at other techniques for generating gain, or other pump types, all right? And this one here is what do we call the electron collision pump. This is the pump that depends on electron collision to create the population inversion. Again, I'll show the three-level system, you know, our basic system. But now the pump is not light, it is an electron. So the idea here is to get an energetic electron to collide with the atom A, here with this gain atom, with the A, and takes the atom from the ground state into this excited state in level 3, so that you have a population difference between 3 and 2. So you can get lasing on the 3 to 2 transition. In terms of an equation, we write it like this. In a simplified form, we take atom A, which means it's a ground state atom A, colliding with an electron with, say, energy E2. And after the collision, the electron separates again from the atom, but leaves the atom in an excited state. Through the collision, the electron was able to transfer some of its energy to the atom and excites it. And then the electron, of course, gives up energy and leaves with energy, in this case E1, which is smaller than E2. So a neutral ground state, or shall we say a ground state atom, colliding with this energetic electron, then can be excited to this excited state here with a population inversion with respect to level 2, leaving the electron with lower energy. Now, of course, you have to tailor the right energy of the electrons with the right atoms. Obviously, that's I don't need to overemphasize that. But when you find the right system, that's basically what's going on. And in this case here is, let's say, a discharge tube. And in this particular case, by the way, lasers work like this on pure electron collision, the argon laser, krypton laser, xenon, nitrogen, copper, vapor, and so on. There are lots of lasers that only depend on electron collision for their pump. All right. So you see here, I didn't mention helium neon because I'll get to it in a couple of minutes. But basically here this is pure electron collisions, and so you need a discharge. You want to generate the electrons and then the right energy, and then you put the right atoms in here, and then you can get the population inversion. You can do it through, as I say, through a discharge or through electron beams and so on, but that's not the issue. The principle is that it is an electron that's colliding with that atom and causing this, this population inversion. Now, the next one is what we call atom collision. All right, atom collision that causes the gain. So what goes on here? Well, in an atom collision, by the way, every time I say atom, I mean also molecules, so don't hang me for not saying molecules when I say atom, especially the chemists here like to use molecules instead of atoms. Well, let's back to our gain system here. Here's atom A with all the ground state atoms. Now, in order to get it up to level 3, this is not now electron collision, this is atom collision. We collided with an atom B in the excited state. Because if you just collided with atom B in the ground state, the two of them are not going to create much energy in atom A unless B is going so fast. So generally, nothing much is going to happen. Maybe A will start moving faster and so on, but really it's not going to be able to excite it to level 3. So what you need atom B to be in some higher level here, where we call the metastable state, M for metastable. Now, when you get a B in this level, collides with atom A, okay, that's what we show here, B metastable, colliding with atom A in the ground state, then you can, and if the energy level of this metastable is close to the energy level here, 3, E3 here for in atom A, then there's a good chance that you will get excitation. Which means what happens here is metastable level in B colliding with A, and as a result of this collision, B goes to the ground state and A goes up to the third level. In a way, what they do, they exchange their energies. It doesn't happen in every collision, but if there are more of B's than A's, then you'll get a net effect is that there will be some A's excited to the third level. Because in a collision like this, there's a whole confusion when the two atoms are close to each other, and they end up, when they separate, in this particular case, there's a good probability that A gets excited and B loses its energy. And as I say, this is maximized, or it's optimized, when the energy of this metastable level is close to level 3. All right? So that's basically the principle. The question now is, where do you get metastables from? And what are metastables in any case? Well, metastables are levels excited levels that take a long time to decay. So there's not something magic. It's just that, before we said there's spontaneous emission, and spontaneous emission depends on the strength of the interaction or the coupling between these two levels. It can be very fast, or it can be very slow. Or sometimes it just doesn't decay at all. There's no spontaneous emission. So if you look at the decay time, if you put, let's say, 1,000 atoms in, let's say, level 2, and you watch them decay, then depending on this coupling between level 2 and level 1, they can either decay very fast or not decay at all. All right, this shows the decay as a function of time. And that depends, let's say, on the lifetime or the relaxation time between level 2 and level 1. This is basics of atoms or molecules. Now, we call a metastable state when the lifetime is very long. What does it mean very long? Longer than a millisecond or so is usually called very long. But they can be much longer than that. And so if the lifetime is very long, then we call it a metastable state. All right. Now here I also have it in terms of instead of time constant, I have it in terms of relaxation rate, which is 1 over the time constant. So when the relaxation rate is then very high, then the lifetime is very short, and when the relaxation rate is small, then the lifetime is long. Okay. So that's basically then the metastable state. Now comes, how do you then generate a metastable state? All right, we're not done yet. So how do we generate a metastable state? Then let's say this is the metastable state that we want to generate. So what we can do, we can use a pump, or some excitation mechanism. It could be optical, it could be electron collision, it could be whatever. And then we can go up to level 3 in this particular case now, in this B atom now, not A. And then let's say by spontaneous emission we come down to here. Then now we've created atoms in this metastable state, and because the lifetime is long, then they're going to stay here. They're going to run around with energy in this level. And then when they collide with atom A, then we get that excitation. So this pump, as I say, can be any kind of pump. Sometimes, we could have direct excitation, again, depending on the particular system and the particular pump. So now we've seen how to generate a metastable state. So let's go over it again. So we first have we have to generate the metastable. So the equation for that is, let's say, atom B. And this particular case, let's say I'm going to look at electron collision. And like in helium-neon, for example, now we get to helium-neon, or the carbon dioxide laser, CO2 nitrogen, or helium-cadmium, and so on. All these lasers depend on atom collision or molecule collision. And basically, they're done, at least the simpler versions, are done with electron excitation. So you take, let's say in this case would be helium. Helium is B. And helium, in the case of helium-neon laser, and you excite it with electron in a discharge, and then you generate helium metastables. And then these helium metastables then collide with neon. In this particular case, A is neon for the helium-neon laser, with neon, and that generates neon in the excited level here with a population inversion. Once you have a population inversion, you have gain at this frequency, and if you have more gain than losses, then the cavity, then the laser takes off. All right, so that then explains the helium-neon laser. Of course, in the case of CO2, it's the nitrogen that supplies the metastables to excite CO2. And in the case of helium-cadmium, again, it's the helium, just like in here, the helium that supplies the metastables to excite cadmium. And there are other kinds of lasers that depend on these collisions. Another type of pump is the chemical pump. All right, now chemical pump. Now we're getting into a lot of tricky treatments here, but I just want to be very brief, as you can see in this kind of a course, without any real math and detailed explanations. Now, a chemical pump is when again let's say the B2, let's say we have a molecule B2, and we either chemically or whatever, we interacted with, let's say, atom A. Could be A excited or A energetic or so on. Or what can happen here, that when A interacts with B2, you can generate, sometimes you can generate, if you know your chemistry, right, you can generate now a new molecule that's made up of AB, and this new molecule is born, so-called born or created, in the excited state or in a state where you have a population inversion. All right, so again, as a result of a chemical reaction between these two molecules, you can create a new molecule that will have population inversion, and then the lasing will take place at the transition where there is gain. Another type is where you start with an excited A atom, energetic A atom, and colliding with a BC molecule, and then creating again an excited state or a population inversion in AB molecule, and so on. And this can get very complicated very quickly. But the idea is that the gain medium comes as a result of a chemical reaction rather than just a pure electron collision or optical pumping. The types of lasers that are like that are HF, hydrogen fluoride, deuterium fluoride, argon fluoride, krypton fluoride, and so on. These are all basically depend on this kind of interaction. Now, one more laser I want to mention briefly, and that's the semiconductor laser, which depends on what we call electron current injection pumping. And again, it's a complicated laser to explain quickly, but basically all I want to show you here is a simple diagram of such a laser. It's one of the smallest lasers there is, and basically it's, as I say, it's current injection. You're passing current through essentially a PN junction, it's called the active layer, and over here you get the gain generated, and the mirrors are actually the reflection the Fresnel reflection at the surfaces, because you have air and the medium, and if the index is high enough, you get about 35% or so reflectivity. So you don't have to do anything. All you have to do is cleave them, and then you get plane parallel cavity lasers. If you apply the right current, you can get lasing. You have a little threshold here, and it comes up. And these lasers, as you know, they're used for all kinds of things today, and now they're also used as optical pumps for other lasers. And I think my time is running out. That's why I'm hurrying up. And so at least in a way, I've exposed you now to the various types of lasers, so you don't have to be too puzzled when you hear about a laser. All you have to ask is what is the pump, and how does it create a population inversion, and then you have to know how much gain you can get, and then with that you know how much power you'll get, and so on. But for that you need to consult the books and go into more depth.